high threshold, showing a loss of devegetation is matching the results in the Global Forest Watch quite nicely. So this is an example of what can be done for a land change. And another example, and this is one we've recently been working in Africa and Tanzania. This is urbanization in Dar es Salaam. So this is 16 years. On the left, you see the urbanization is in the darker red areas. This is a bare soil component of a fractional cover product. And on the right side, you can see the increased urbanization 16 years later. This particular area has grown 7% per year using this threshold approach with a population growth of 5%. And if you are familiar with the UN Sustainable Development Goals, this basically says that the urban areas is expanding quite rapidly related to the population growth. So finally, to show you where you can find the Open Data Cube resources, I've listed a few things here. The best place to go is our Open Data Cube website. So just opendatacube.org will take you to the top website. Once you're there, there is a sub-menu for installation. There's another menu for applications. If you go to opendatacube.org-dcal, D-C-A-L, which is DataCube Application Library, you will see some of those 6 tools that I showed you, the 6 primary applications we have, as well as links to the YouTube videos. We have some nice documentation that is also available on the website, but this is a link to take you directly there. And we have a GitHub where all of the open source software is available for your use. And then finally, just a repeat of that user interface. If you'd like to play around and see what the DataCube can do in terms of a web-based tool, the tinyurl DataCube UI is the place to go. So I'll stop there and just say thanks for the opportunity to be part of this, and I'll entertain any questions as we move ahead. Thanks, Doug.
Yeah, thanks a lot, Brian. So just to kind of recap here, the Open Data Cube is a very sophisticated tool to allow you to do time series analyses, being pixel precise, and it is particularly well suited to use with Amazon Web Services and their cloud computing facilities. I myself have had the chance to play around with it a little bit. And one thing I wasn't aware of, you said by the end of 2019, USGS will put all of their Landsat data. So that's going back to 1973, is that right?
I'm not sure I think they're focusing on Landsat 7 and 8, but I do believe 5 is in there. So they'll probably take us back to the mid-1980s.
Okay.
I don't know if anybody from USGS is online, but I believe the current plans are by the end of this year to have all of that data on the AWS in S3 buckets. And I believe it will be a combination of the level 1 data, which is the unprocessed, well, it's level 1, it's been geo-rectified, and then also level 2 surface reflectance products for the globe, which I think is just a fantastic opportunity to have this data in the cloud.
Great. Okay, so for those of you listening and those of you who are planning to submit a proposal to make use of the cloud credits that we're offering, here is one very sophisticated tool that you could use. As Brian has demonstrated, you've got a number of analyses that can be done, water extent, urbanization, and so forth. So keep those things in mind. Now I'd like to save your questions. As I mentioned, I would like to go through the 4 presentations first, and then as time permits, afterwards we can entertain your questions. So if you've got one, either write it down or put it in the chat window and we'll try to get to it afterwards. So next up will be a presentation from Grega Milczynski from Sinergise, and he's going to talk to us about Sentinel Hub, cloud driver for EO data. So Grega, it's all yours.
Just to confirm, can you hear me well?
Perfect.
Okay. So hi to everyone. So I'm Grega Milczynski, as mentioned. I'm coming from Sinergise, Sentinel Hub. And now Brian has showed tools how to create analysis-ready data and how to exploit them. And what I want to focus is in an alternative option, making use of the Sentinel Hub as a kind of the cloud API to get similar results directly from the service. And Amazon, I believe, has done all of us a great favor of putting all this data from Sentinel, Landsat, MODIS, and so on to the cloud infrastructure so that we can easily and in a performant manner access to this. And I think this is really something that was never possible until now. However, it's still not really straightforward to work with this because you have large amount of data, you have different formats, you have different projections and so on, and all the complexities of the remote sensing data that people simply are not familiar and comfortable to work with. And this is where the Sentinel hubs come in because what it does is it hides this complexity behind a set of OGC compliant web services and an APIs, which basically expose all these data that are available on Amazon to various kind of GIS applications, either desktop like QGIS or if you want to do the Python machine learning workflow, if you like. So, basically what it is an API which you access in a similar manner as you would access the S3 interface, but instead of going to individual file, what you say, I want to have this and this specific layer, I want to have the layer from the specific time period in the specific area of interest, and then some additional parameters like resolution and so on. And all of this basically, when you do this request, then the service behind it does all the decoding, the mosaicing, reprojection, auto-classification, if you like, all these things that you would need to do yourself, or the tools from the data cube would need to do to make it analysis ready. And basically, when there is somebody with a voice, by the way, who should be muted maybe. Okay, perfect. So when getting an access to the system, you enter into configuration utility like what we see here. And here you can configure the layers that you'd like to use. For each layer, you can simply choose which data source it is based on, like Sentinel-2 Level 1C or Level 2A or Landsat or something like that. And then you define a processing script. You can choose amongst like 200 different options that are already in the system. But what most of our users do, they simply do it themselves. So they put in the algorithm, and then they write how they would like to output it. And then you simply test this, how it looks like. And then if you like, you even get the code snippet to create an application, or rather you get the URL with the WMS service where you can access this data. If you're using QGIS, there is a QGIS plugin available, which also supports different kind of like switching between dates and so on. For advanced users, there is a dedicated API which makes it possible to use this and many other things, and really gives you full control over what's happening with the data. And you have all the power of previously demonstrated, but with really full control. Through Sentinel Hub, you can get data either as like original reflectance values, if you like 0.7 for each pixel or something like that. You can get it visualized in a polygon, or you can get statistics for the long time series, as we see here on the right bottom corner. Now, this processing script is something that users are very fond of, because it makes it possible to simply configure what you'd like to get out of the system. So, in addition to these standard things like true color, false color, NDVI, and so on, you can basically define your own combination. It can be, I don't know, you can ask for 13 bands of Sentinel-2, or you ask only for 3 that are false color, or you can create a NDVI index or any other algorithm. Even, more complex one like a leaf area index, which is a neural network. It's something that you can simply configure in the system, and you get it out immediately. And because there are so many of these algorithms, we created a repository of the, we call it custom scripts repository, which is in GitHub, and it's open source. And you can access through all of the processing algorithms that we already have in the system, and users are entering more of that. And for each one, you have like the algorithm and then some visualization options, which you can then configure however you like it based on your own needs. Now, with the service, then you can do in a matter of minutes, really, an application like this Sentinel Playground, which probably most of you are familiar with, where you can get access to complete data set, complete archive of Landsat, Sentinels, MODIS, and so on. And so I'm talking both the archive data as well as the data that were only acquired a couple of hours ago, right? I mean, it takes literally 30 minutes to 45 minutes to get the data from the hubs, from the Copernicus hub to Amazon, and then immediately they are available through Sentinel Hub. And I mean, again, this application that you're looking at is something that you can build by yourself. It's open source. You can simply configure it and customize it for your own needs. Or even more advanced things like, again, your browser, which, again, most of you know. For those who don't know it, I suggest that you take a look at it because it allows a very easy way to browse on which data are available. But as a tool itself, I mean, what is important is that, again, this application is open source, so you can go to GitHub, you can download it, and then configure it for your own use and for your own need, doing like time lapses like this and so on. So I think this is important, that with this kind of processing scripts, you can really do something that previously took days or weeks to process and to download and so on. Now you can do it literally in a matter of seconds. And because it's so fast, you can do the prototyping very fast. So you can literally do the whole system in a matter of, I don't know, a couple of hours. There are some advanced features available, similarly like what Brian was telling on the functions of the data cube. So if you want to get the maximum NDVI, there is a function for that, which, by the way, it's not a function of the system. It's rather just another custom script which you can then configure yourself. This is an example of the normalized burn ratio before the wildfire, after the wildfire, and then again you can do a custom script like this one, compare it, and then you get results as which areas were more damaged and which less. Sentinel-1, which is a bit difficult to work with because it's radar and because the GRDs are non-auto-rectified. So we help with this as well. So you can simply set up a parameter to auto-rectify data, and you get through the service already auto-rectified. And you get basically you can get a gamma knot directly through the service based on the Sentinel-1 GRDs which are lying on the Amazon. So we support basically all the major data sets that are available on Amazon: Sentinel-1 GRD, Sentinel-2 Level 1C, and Level 2A. Here it's important to know that Level 2A are those that are processed by ESA, meaning that they are available from March 2017 in Europe and December 2018 globally. If somebody needs some additional Level 2A data, we can pre-process them and make them available through Amazon again and through the Sentinel Hub. Then Landsat MODIS digital elevation model is interesting for many things, amongst other the auto-rectification of Sentinel-1. And we are working to add more of these data sets. And just to give you a feeling on this service, I mean, it is used pretty regularly. We process between 3 and 6 million requests per day. So whatever you would do with it, probably it wouldn't make much of a dent. And we process 5 petabytes. We basically make available 5 petabytes of data through the service so that you don't need to browse through it. Very important point that the service is fast. Like vast majority of the requests are processed in less than half a second. So that means that you can integrate this directly in the application that you are building without the need to store the data on your side. I mean, if you are doing something advanced machine learning, you will probably do some pre-processing and then put it on your servers and run it there. But for the applications, you can simply integrate it in the app, and then it will be only processed when needed. Because there is so much of data available, we started to think on how to exploit it better. And we realized that all the existing frameworks like TensorFlow and MXNet and so on, they're not really fine-tuned for the satellite data and the complexity of clouds, hazes, the shifted pixels, and so on. So what we did is we did an open source Python package called TioLearn, which basically allows you to set up a workflow to prepare the data in a way so that it can be then easily used by TensorFlow. Or you can use it for random forest or LightGBM or whatever. I mean, all the machine learning processes can simply be run with that. and it's extremely efficient because I mean it works in the cloud and it works only when needed. And I mean, as an example, we have set up a automatic land cover classification method on the country scale, where there is a Jupyter notebook available with the complete workflow from start to end, from the ground truth data to the validation of the results. And we wrote like a 3-part blog post to explain each and every step, which is probably a very good way to start if you're going into this field for the first time. The results are pretty good. Here you can see the example of the automatic classification and on the manual labeling. But again, the important point is that this is open source and you can just take it, configure it, and improve it if you like. Another example of how you can easily use the service and the data, we tried to replicate the system that Joint Research Center and Google built a while ago to kind of make the availability, to present availability of data in specific areas. And we did the Blue Dot Water Observatory, which basically does exactly this, right? For all the water bodies, surface water bodies in the world, the ones that we found relevant are every time that the new Sentinel image comes through, we process the image, we identify the extent of the water, and then we put it in the database. And again, this workflow, I mean, this is important for 2 reasons. One is that obviously it shows the usefulness of the data for a specific use case, but it's also important that the whole process costs about €6 per month because it is done in an efficient manner, right? Because it only takes the data that you need, and because it's running in the cloud using all the Lambda functionality, which is very useful in terms of the cost perspective. And again, all of this is open source, so you can take this workflow and you can configure it for your own use case or your own area of interest. To conclude, I believe that it was really never easier to exploit all this Earth observation data. I mean, thanks to USGS and Copernicus first to having the data available, and then to Amazon to make the data available in the cloud. So it's really easy. And with Sentinel Hub, I hope that we demonstrated that it's even one step easier to start with. And if you want to try it, you can do it actually like immediately, going and creating a trial account with all the functionality. And now what is important to note is that Sentinel Hub is an additional service. It's not part of the core Amazon services. It's an additional service, and we made an agreement with GEO to also make this service available to all the applicants of the Amazon GEO program. So whoever is applying for Amazon credits and you would like to use the Sentinel Hub as well, just mark it there in the application that you want to use Sentinel Hub and approximately the volume that you'd like to use, I don't know, the area of interest that you will be processing and so on. And last but not least, most of the tools that I have shown are open source, available on GitHub. So you can simply take them, use them, and hopefully also contribute something back to the community. And I'll conclude here. Thank you very much.
Great. Thank you very much, Grega, for the interesting presentation. So again, what Sentinel Hub is it's an API that allows access to large amounts of data. You can custom process what it is that you're looking for, and we thank you very much for the generous offer of giving some credits to use Sentinel Hub. So please, those of you who are thinking of submitting a proposal, bear this in mind, and we can provide you, answer any questions you might have, either if we have time later on today or else by email. We can handle that. Okay, so now I'd like to move on to Hamed Ali Mohammed of Radiant Earth Foundation. He is going, I hope he's online. Let's see. Yep, there he is. So he's going to speak to us about the Spatio-Temporal Asset Catalog tool called STAC. And as he's getting prepared here, there were just there we go. Okay, very good. So Hamed, it's all yours. Go ahead.
Thank you, Doug. Can you hear me well?
Yes, just fine.
Hello, everyone, and thanks for joining us today. My name is Hamed Ali Mohammed. I'm the lead geospatial data scientist at Radiant Earth Foundation. We are a member of GEO, and also when we started about 2 years ago, we were also a recipient of the AWS nonprofit credits. So we have been working with both GEO and AWS for 2 years now, and we have been benefiting from all the resources they have been providing. So happy to be here and share our experiences and talk about two open source toolboxes, Stack and MLHub Earth, and how you can benefit from them with the projects that you have and taking advantage of the new credits program. To start, I will just give you a brief 2-minute overview of what is Radiant Earth. We are a nonprofit organization based in the United States. We work to provide access for open geospatial data and tools and analytics around that to the global development users. We want to enable those users to address the challenges they want to work on and basically provide a free service for Earth imagery, including satellite and drone and airborne imagery on a cloud environment. Currently, we do this with different kind of pillars of our program. The key part is the technology platform, which is sitting on Amazon Web Services. It provides access to different satellite imagery. You can upload your own imagery if you want to access and do analysis on that. You can share it with your teams and colleagues inside the platform, or if you have an analysis you want to share it outside of that, you have that functionality. We also have an active community development program that we provide educational and kind of geospatial tool and analysis on our kind of Medium blog posts, on our workshops that we host, and also regular infographics that we publish on our website and through our newsletter. And a small chunk of our work is around consultancy, which is more on the capacity building, working on specific use cases with partners and basically developing new tools and applications, which all of them are open source, and then basically showcasing the capabilities of these open source data. You can access our platform on this web address, app.radiant.earth. Feel free to check it out at any time. It is a self-service kind of sign up. You can start exploring the whole archive of Landsat 8, Sentinel 2, the MODIS data, and also archival Landsat from Landsat 4 to 7, as well as any other geospatial, raster data that you might have and you want to upload and start exploring. If you have also data sitting on an S3 bucket, you can directly connect that bucket to the platform and start visualizing and exploring your data. And for those of you who might be interested into a more API access with programming interface, you can go to doc.radiant.earth and see the documentation for the API and instructions onto how to access the platform. With that, I would like to start with talking about Stack. So Stack is the abbreviation for Spatiotemporal Asset Catalog. And as the name resembles, it is about geospatial data, and it is about data that is that has a spatial and temporal features. And the first question might be, okay, why we need such a catalog standard? As you know, as you might have explored satellite imagery and in general any geospatial data, searching for data is hard. For any kind of data, you need to go to a different portal. You need to include different kinds of parameters and features. Each of those portals have an API which have a different standard. All of them are useful, but when you want to search in a kind of global space, you need to go to different portals, and it is time consuming. And as a user, one needs to build kind of unique pipelines for each of those APIs. So it would be better and ideal if we could have a standard API to search against all of the catalogs globally. That's why initially Stack was born, and Radiant was basically the thought leader behind the Stack. It was a community effort, and it is still under active development as an open source technology. And the idea is we want to have an open specification basically to increase the interoperability of searching for global data. And these are all data that has spatio-temporal features. So you can think about satellite imagery, aerial and drone imagery. You can think about derived products, like if you have a land cover map, if you have a water mask derived from satellite imagery, or any kind of alternative data sources like LiDAR data, SAR data, hopefully in future more of the full motion video data, and also hyperspectral and any other kind of geospatial data. Stack has been, as I said, a community effort. Different groups from the commercial side, from the nonprofit, and also data providers like USGS, NASA, ESA have been contributing to this catalog, and now it is being adopted by many of those agencies, and it will provide that interoperability that originally was designed to. I will give you a very high-level kind of diagram of what the catalog look like. So at the top level, you have one stack catalog. Inside that, you will have like a collection of data. That collection will have features like an extent, what is the geographical extent of data in there. It will have a provider. Then there will be an item inside the collection, which in practice, it's just a GeoJSON file describing your data. And then that item will have features that you would regularly think about them, like a geometry, a bounding box, some properties that depending on the item type, whether it's a optical imagery or a SAR data or a derived product would be different. And then an asset, which is the list of links to the actual file, whether it's a GeoTIFF file, a JPEG 2000 file, or a cloud optimized GeoTIFF or COG as we call it. And as I said, the properties basically would define that type of data. One thing that was put into Stack development from the beginning was simplicity. So each of the basic cores are defined in a way that you can extend it easily to different data sets. So as you see, until the level that you have the properties, there was no mention of what is the type of data. So in this level, you will define it, oh, this is an Earth observation or a multispectral data, and you define the properties related to that. That makes the interoperability of these catalogs and also searching against them much easier and understandable kind of to different APIs. This is again the core level kind of metadata that goes to the collection level. As you see, it's the Stack version. We want to know which Stack version is being used, an ID, a description of the data, the license that is applied to that data, the extent and the links, and some other kind of optional fields you can add like keywords and providers. When you go to the item level, you have more kind of detailed metadata there, like the geometry is included, the bounding box, the properties can be like a dictionary, you want to add different things, which includes the extension, and the links, which is kind of an object to the resources and related URLs. All of these are on GitHub. I will show you the link. And what would be beneficial to you is benefiting from the Stack catalogs currently being developed. Some of the data on Earth on AWS currently have a Stack catalog. New data providers are converting their data or adding at least a Stack catalog to their data so you can search against them. If you are producing new products, whether it's a derived product or capturing new imagery, you can publish them as a Stack catalog and benefit from many of the resources available out there. And this is showing the extension specification, basically the metadata applicable to the Earth observation data, which is the multispectral imagery. You can think about the ground sampling distance, the platform which is providing that, the bands and projection, and so on. So all of this is sitting on this GitHub repo, github.com, Radiant Earth, and then stack-spec. If you go to the Radiant Earth level, you will see a list of different kind of items and projects there, but the Stack is one of the very active ones being developed. If you want to also contribute to the Stack, feel free to join the conversation on GitHub. If you have implementation of the Stack, you run into any issues, feel free to submit tickets, and then the team will follow up with you. There's also the Radiant Earth Insight, which is our Medium blog post that one of our fellows, Chris Holmes, regularly writes about the developments in the Stack, and you can follow his writings and see what is the latest developments in there. To give you a sense of what does it mean to use the Stack in action, I'm going to show you one of the Stack catalogs, which is sitting on Amazon Web Services now, and the catalog that we are looking on the web. So this is now the browser. So I went to this URL, iserve.stack.cloud. Basically, this is a browser to see and basically explore this catalog of imagery. So ICERV was a multispectral camera mounted on International Space Station for 2 years. It captured imagery in RGB bands at 5.6 meter spatial resolution. And we, Radiant Earth, basically converted that catalog to all of the data being cloud optimized GeoTIFF, and also with the stack catalog now being hosted on Amazon Web Services as an open source data. So you can see the kind of different descriptions of the data here, but down there you will see basically the actual catalog with the JSON files. So let's see, for example, let's open one of the data in 2013. Then there's the month March 27th. It shows the bands that are available at this level, and then the items, which are the actual cog files. When I click on one of them, it will show me the preview, which in this case, because it's a cog, if I actually zoom in, it's the actual data that I'm visualizing right now directly from an S3 bucket into the browser. So we are basically streaming the data into browser in real time and exploring that. You can use the same kind of interface and have an API call to that data, and the stack catalog will help you find and basically filter the data. You can access the thumbnail, different assets that data has, and also, again, the band information for that specific item that we just visualized. There are different implementation of this Stack browser. So Stack browser was another kind of open source technology that developed, and it is sitting on our GitHub. You can check it out. You can, if you have another Stack catalog, you can use the same open source catalog, browser, and visualize your data. There are other implementations of the Stack browser as well. So the second topic I want to touch on is around MLHub Earth, which is basically an open source set of commons for Earth observation data. We at Radiant, working in the global development, have come numerously across this issue that a significant barrier exists in terms of people using more machine learning techniques to address their challenges, and that is the lack of training data and kind of benchmark models. Many of these efforts are effortful, so you need time and resources to generate those training data, and if you want to have them specific to a region or at least globally diverse, it takes some resources. So we have established MLHub to basically catalyze different efforts and also kind of democratize this space for better applications of existing training data, and also putting some effort into producing new resources for training data and models. So MLHub will be basically a two thing. One is an actual repository for training data, which will be hosted on Amazon Web Services S3 bucket, and also a registry for training data that other providers might have produced, but it is sitting on their own repository. But if it has an Stack catalog, which we will have an Stack extension for training data, we will be able to search against those and expose them to the user. So it will help all the users to access these data better. In the phase one, later in the summer this year, we will publish 2 training data sets on MLHub. One is on global land cover classes, and the other one from major crop types in Africa. Both of these will be based on Sentinel-2 data at 10 meter spatial resolution, open source data, and in a very much ML-centric way, meaning that we will generate kind of image chips with layers of labels that easily can be read into a machine learning algorithm. Mid-springtime, which is about a month from now, we will also operationalize a label generator dashboard, which will help users go to our platform, which I mentioned, the app.radiant.earth, annotate their imagery, and then come to this dashboard, validate those if it's a crowdsourcing effort, for example, and then automatically publish them as a Stack catalog in MLHub. And also an API that would let you search against all of the existing training data on MLHub. And all of these are open source. It's toward the end of the development. I mean, this would be kind of a screenshot of what would the tool look like. For example, here I'm looking at some pivotal forms and also a rectangular one. I have used the annotation, labeled all of them with form. You can add also descriptions. And then you will come to the second dashboard, which is the validator. You will have a set of tasks to validate if each of these grids have the correct labels, If not, you can correct them, delete them, or add more, or change the description. And when you basically save this project, it will publish a catalog on MLHub Earth on S3 bucket. We will keep the community posted on the recent developments about this. You can follow us on Twitter and also our Medium blog post. There's also our Facebook group, which is more focused on our users as a community to share their projects and experiences. But follow us and you will hear the news about these latest MLHub tools being open source, and also the links to our website, the app that I mentioned, app.radiant.earth, and our GitHub repo, which hosts all of the open source toolbox. Thank you.
Okay, thank you very much, Hamid. So some very interesting tools there, the Open Geospatial Data Platform and its API that searches all catalogs for increasing interoperability. And then also MLHub, which is a source for training data, models and best practices. So again, please avail yourselves of these tools. Now we'll go to the last presentation, which will be given to us by Amy Barklauskis, I think, if I got that right. Sorry, Amy, if I butchered your last name, from Development Seed, and she will be talking to us about open source tools for managing planetary scale data on the cloud. So Amy, it's all yours.
Hey, yeah, thanks. Can you guys hear me okay?
Just fine, thanks.
Okay, great. Yeah, so today I'm going to be talking about how we at Development Seed are managing planetary scale data on the cloud in collaboration with NASA and some other organizations that we work with. So we at Development Seed, first to introduce who's going to be talking today, that's me, Amy. I'm a data engineer at Development Seed, and also Ian Schuler, who's CEO, is going to be talking a little bit later on. So Development Seed is an organization that works with organizations like NASA and the World Bank and WRI, and we work on both sides of the equation. So basically managing data archives, basically ingesting those data archives and creating workflows to ingest, process, store that data on the cloud, create the data products that power the applications. And then we also work with organizations to create the applications that help support decision makers using Earth observation data. And then I'm going to pass it off to Ian to introduce himself as well.
Hey guys, this is Ian Schuler. Amy, just a quick flag. I think if what we're seeing is the intro slide. If you're going through, it might be on a different screen, so you might need to kind of tab through on the Google Docs itself or Google Slides itself in order to get it to change. I've had this issue before, but hey, just wanted to say real quick. Really happy to be here, very excited to be part of this, and particularly because of the caliber of some of the other presenters that y'all are working with. We've been working with all of the groups that have been mentioned and have a lot of respect for the products that they've talked about. Some of the things that we're going to talk about today are actually integrated into the Sentinel Hub work that Greg had talked about and into the ML Hub's work that Hamid talked about. Also want to give a strong shout out for Stack. We use Stack internally for a lot of our catalog work. If your project will involve creating sets of data, new novel sets of data, I strongly recommend looking at Stack as a way of creating a metadata catalog for that. What that will do is open up a lot of tools that are being built to be able to immediately be able to work and play with your data. So I just want to reinforce Hamid's shout out for that. And then also to kind of talk a little bit about where we differ from some of the other things that you've seen. I mean, I think basically the other tools you've seen today are all fantastic. If any of those work for your needs and what you're trying to do, you should probably use one of those. What Amy and I are going to be talking about is a little bit more the case where those things don't actually give you the level of control that you need. Probably if you're using one of the tools that have been mentioned, you are building something, your project's really targeted at GIS experts, data scientists, other people who just want to be able to get at the data and have a set of tools that they're familiar with for working with those. And the cases that the Cumulus stack and some of the other things we're talking about might make more sense is where you want to create an ongoing data product, a higher level data product based on your own algorithms, a yield projection for a crop that's specific to your area using an algorithm that you created, or biomass estimation using in situ data that you created, and to do that in an ongoing way. Or if you want to have deep earth science research that needs more ability to manipulate the data than is being offered natively in some of the other tools, then you might need to set up your own stack that allows you a little bit more control over how the data is processed and managed. And that's where some of the tools that we're talking about may end up being a little bit more helpful for you. All right, Amy, back to you.
Cool, thanks, Ian. So with that, can you guys, so you're seeing the introductions with these nice black and white photos of myself and...
No, I'm seeing at least the Google Docs.
Okay.
Because I think it's showing the other one on another screen. So maybe just if you...
Okay, let me try again. Oh, I see.
Yeah, this is a trick with, I've seen, there you go.
Is this, okay, this is better?
Yep.
Perfect.
I see.
Yes, great.
Okay. I'm a blue jeans noob, so thanks. Okay, so now you can see our beautiful faces, and I'm going to move on. So yeah, so we work with NASA, and NASA has always, one of the reasons why we love working with them is because of their commitment to open data and open source software. So since 1994, the ESDIS the Earth Science Department has been committed to the full and open sharing of Earth science data. And as you guys might be aware, there's this data archive is growing hugely, exponentially in the next couple of years, and basically it's going to experience a 10 times increase between 2017 and 2022 due to some upcoming missions such as NISAR, which is going to be ingesting, petabytes, I think petabytes a day. And they saw this upcoming big data evolution, and they said, we're basically not going to be able to, given our current paradigm of how we ingest and manage this data archive, we're not going to be doing our users any services by continuing to follow the existing system, which is sort of an on-premise system, and it's not going to enable us to actually make all of this data available and usable by end users. So with this, it developed, it sort of embarked on this new this new journey of the cloud evolution. So basically looking at how they could integrate with a cloud provider, that cloud provider being AWS, integrate that cloud provider with their existing data centers, these DACs that you see on the right and the left here, these distributed active archive centers that were existing to already ingest and process that data. So they already have their existing processes. How can we basically integrate with those DACs and their processes to provide all of that data on the cloud in a format that end users can use? And what is a uniform way of doing that? So basically out of this came the Cumulus project. So the Cumulus is a piece of open source software that I'm going to talk a little bit more about as we move forward. But basically the general idea is that it's a piece of software that enables anybody, but specifically the data centers, to distribute and process their data on the AWS cloud. So what is Cumulus? So as I mentioned, a little bit of background. If you're not familiar with distributed active archive centers, there's 12 of these active data centers, and they all have different thematic focuses, science focuses, and they're located across the country. And they've been managing and processing and creating applications off of this data for many years. So Cumulus is basically working with those data centers to, you can see Cumulus is the second layer here. Basically, it's working with these data providers, these data centers, and these staging centers to ingest and process all of that data and put it on the AWS cloud. So this is just an example. So one of the applications that you might be familiar with is NASA's Global Browse Imagery, so NASA's GIBS. And this is an example of just showing basically how GIBS was able to move its existing sort of complex data workflow into an AWS step function. So Cumulus is very much relies on AWS step functions, which enables you to create these complex workflows for your data processes. So this is a little bit more into the nitty-gritty of how Cumulus works, but what I really wanted to basically emphasize with this slide is that Cumulus is built on a number of different AWS services, and that is really what makes it powerful. So Cumulus is powered by the fact that AWS itself emphasizes things like the ability to be configurable and the ability to be serverless and the ability to basically scale to any workload. So put very simply, Cumulus is a collection of resources for deploying and configuring a data pipeline in the cloud. So when I say Cumulus is a collection of resources, it's basically a bunch of different modules that you can sort of put together depending on the different types of workflows that you need. So you might need to create a new data product, or you might just need to manage your existing data products. Cumulus has a number of different libraries that you can basically piece together to create the infrastructure that you need for your data management and archive system. So why would you use Cumulus? Well, because it does leverage a lot of really great AWS services. For example, AWS Lambda, AWS step functions. These are serverless technologies, and this is really great from a development operations standpoint because it limits security risks associated with managing servers. It scales and is fault tolerant out of the box. Cumulus also features a rich API for triggering, scheduling, and monitoring workflows. It also comes with a dashboard and all that jazz. It's also supported by a large team within NASA's Earth Observation System and Data Information Systems division. So, new feature requests are adopted by that team. And as I mentioned already, it's modular. It has many components and can be sort of configured for your use case. So I want to talk about a couple Cumulus applications. So Cumulus is used, as I mentioned before, Cumulus exists outside of NASA. It's an open piece of open source software, so it's being used outside of NASA. So we have used it with a couple of different partners I've listed here. GEO, as you guys are all familiar, WRI, the World Resources Institute, we were working with them on something called the Air Quality Model Live. So there we're using Cumulus to produce air quality model results in near real time. And then another really cool application is the application that we've built in collaboration with the National Hurricane Center, doing hurricane intensity estimation using machine learning. So this is where Cumulus is actually being used to generate predictions of hurricane intensity using GEO's imagery. So if you're interested to learn more about how to use Cumulus and what it could be used for, as I mentioned, Cumulus is open source, so you can just go to github.com/nasa/Cumulus to look at the code. There's also, very detailed and well-maintained documentation about, one of the reasons why the documentation is great is because it comes with, obviously some instructions about how to actually deploy a Cumulus stack, but it also comes with these data cookbooks, so that will give you some example, hello world and more complex data workflows. And then finally, there's a Cumulus API. As I mentioned, the Cumulus API is very rich and comes with a number of different endpoints for managing your data collections, your data granules. So these are links to some of the things I just talked about. And finally, I'm going to pass it off to Ian to talk about some of the applications that we built on top of these data products.
Thanks, Amy. So once you have the really neat thing is like once you have data in a cloud format, whether that's data that you've prepped and prepared using Cumulus or another workflow, or whether you're taking advantage of one of the data sources, one of the APIs that was mentioned earlier, or whether you're using NASA on AWS, you can do some really cool things with that data. Beyond just preparing data and getting on the cloud and using the cloud as a way to make data creation more efficient, one of the things we're most excited about are the different ways that you can use this data once it is enabled in that way. And so one area that we've been doing a lot of work is being able to apply AI on Earth data at planetary scale using data kind of at rest in S3 buckets on AWS. And so there are a few tools that we've developed to make that easier. I mean, the moral of the story is the frameworks for doing that and the actual the AI tools themselves continue to change and evolve, and we keep adopting those. But for each of these, many of these are tools that have been developed originally for photographs, not for overhead imagery. And there's a lot of additional helper work that's needed to create the sort of files that would be useful, that would be needed to use a common machine learning framework, TensorFlow, PyTorch, use your preference. And so a lot of what we built are things that enable that. So Amy, if you can click forward. So Label Maker is one set of tools, an open source tool set that makes it easier, that does some of that preparation of data sets for use in an ML framework. Again, if you're using the ML Hub or EO or Sentinel Hub, a lot of this is built in and comes for free. But if you're doing stuff on your own, you might want to pull that down on your own. Basically what it does is allows you to quickly create a set of tiles, of training tiles, using a small configuration script. So here's an example of one of those scripts. It also integrates with Amazon SageMaker, and my colleague Nana put together a nice walkthrough on how you would use Label Maker to make the work around employing SageMaker for overhead imagery a little bit easier. I'll paste that in the chat afterwards. Cool. So then this is an example of another set of, so part of the challenge of doing ML on overhead imagery is cleaning and when working with the data. There are a number of other sort of helper tools that we've created to make it easier to improve or review your training data and make sure that it's high quality. And then finally, in the next slide, one of the other things I wanted to highlight is a tool called Looking Glass, which uses some newer methods for building detection, and we found has gotten us to pretty high accuracy building detection outputs. That's an open source tool that we've built called Looking Glass, which I'll paste the links in the chat afterwards. Cool. And so the other thing that's really neat about the way that we're working in this is by working with a combination of cloud-optimized GeoTIFFs, Stack Browser. You basically create a light serverless framework for applying ML and for doing transformations on the fly. And so we have examples of essentially being able to do machine learning prediction in browser as images load. This is an example of doing land classification. And then the next slide is an example of doing row detection. And so then this starts to open up whole other deployments for this sort of work, where instead of running a process on an entire imagery archive and coming back in the morning and seeing what the findings are, you can start to enable modes of usage that essentially give decision makers products that do that sort of analysis live on the imagery as it comes in without pre-processing. That has a number of advantages. One, you don't have to have constant servers running. A lot of this is done either in browser or using Lambda functions that are spun up as requested. And the other thing is you can start to do that processing on imagery as soon as it comes off the satellite and don't need to have time-consuming processes that get in the way, allowing you to have more ongoing monitoring or response tools and allowing you to just run ML as needed on places where people care about and not run it over wide swaths of area that people aren't really paying attention to. And what that allows you is to start to make some really interesting products for decision makers. I think that a lot of the tools, the other tools that are out there, are really great tools for scientists, for data scientists, for GIS experts, but the majority of like end decision makers wouldn't know what NDVI is, or wouldn't know what to do that with that data, or wouldn't know how to generate some of the products that are capable or take advantage of those. Part of what we're doing is taking the underlying data and product generation to spit out things that are very specific to the needs of individual decision makers and operators. And so Amy mentioned one example of a tool for estimating hurricane strength. We were working with a group at NASA to, as GOES imagery came off the satellite, classify that imagery, run a machine learning, computer vision process to estimate the hurricane speed and wind strength, to test whether we can produce faster, accurate results for hurricane intensity than is coming through other sources. And so we were able to build a tool around that allowed you to see the current state of things and predictions over time. That was very clear to an end user what was the information they needed. We've done some work on land cover use, land cover classification, that again is able to be managed quite quickly with and can be produced on the fly over imagery as needed. We've done some work to detect power grid, and here that we were able to quickly classify all of Pakistan and look for places where there might be power lines, and then have a human team of tracers just look at those in places where there might be a power infrastructure, and tag that as the case where power infrastructure exists. And so that was a very specialized application that allowed us to map all of the high voltage power grid in Pakistan, Nigeria, and Zambia in a matter of weeks. And then finally, using ML as you load information from OpenStreetMap to show you the current building density in OpenStreetMap, and also what we believe based on a computer vision process, on deep learning process, what we believe the number of buildings in the area should be based on the underlying imagery, to be able to quickly do a diff and see, where are areas that might be undermapped. So if I'm trying to improve the map around a particular city, what are the parts of the city where I should send mappers to or direct people's attention to? And all of that can be done in kind of purpose-driven apps on the fly as needed, based on some of the building blocks and modular components that Amy and I have talked about. Cool. That's all I have to talk about. Super excited for questions, and I'll post some of the links to these in the chat.
Okay, great. Thanks a lot, both Amy and Ian, for walking us through some of these products. So I think that one thing I retained from what you just said, Ian, is that these tools provide a light serverless framework for doing machine learning, and I think that could be a very useful thing to include in these proposals. So now I'd like to open up, in the time that remains, we have about 20 minutes left. There have been some questions made in the chat windows, and so just to recall, those of you who may not be aware of what the Cloud Credit Program is about, you can go to earthobservations.org, which is the GEO website, and then you'll find the information there. Essentially what it is it's a Amazon Web Services is providing cloud credits for proposals that will make use of Amazon Web Services, and then the variety of tools and And in order to solve some particular problem you might have in a developing country towards sustainable development. I was kind of assuming that everyone was aware of what the program is, but there were a couple of questions related to that. So please refer to the GEO website. Again, it's earthobservations.org, and then you'll find it once you go there. Let me try to open it up. We've got 53 people online. Not quite sure how this will work, but let's see if anybody has a question. Go ahead and unmute yourself, and then speak up for any of our speakers or myself from the GEO Secretariat. Don't be shy.
This is Peter. I'm calling from the Netherlands. I just placed my question on the chat. Can you see it? On the situation of developing countries.
Right.
They have.
Okay, so
yes.
Go ahead. Yeah, go ahead.
They often have weak land registries and large numbers of non-registered or called informal farmers or squatters, miners, etc. And having open data has caused conflicts in their societies. Have you talked, have you discussed, have you identified such risks? Thank you.
Well, I guess I can answer from the GEO Secretariat standpoint, and that is we have specified in the application that in the application for the Cloud Credits program, that whatever is developed should be completely open source, open science, and it should be used to address some aspect of sustainable development. And in actual fact, to support the Sustainable Development Goals, one of the 17 goals, or to support one of the articles of the Paris Agreement on Climate, or the Sendai Framework for Disaster Risk Reduction. Those are the three main focus areas for the group on Earth observations right now. And I think from that perspective, I'm not sure that this kind of a situation would arise that you're referencing here. But in any case, we also will be reviewing all of the proposals. The deadline is coming up at the end of this month. And then over the month of April, several of us at the Secretariat and others from the GEO community will be reviewing them. And I suppose if we see an issue such as this, where there's the potential for some kind of conflict, we might go back to the proposers of the project and try to clarify that.
Thank you. Last year there has been a conflict, quite a big one, between Indonesia's government and WRI using the Global Forest Watch. Are you familiar with the conflict? I mean, there was a large difference in number on forest and deforestation and what caused it.
Mm-hmm. I'm not familiar with that particular conflict, but I'll take a look at it. The Secretariat Director right now, Gilberto Camara, comes from Brazil, and he was actually the director of the Brazilian Space Agency for a number of years. So he's very familiar with forestry monitoring and the issues surrounding that. So I think he would be he'd be a very good resource to help try to understand if there's a potential for conflict in a proposal.
Thank you.
Yep. Okay. Another question that came up in the chat window here, I see. I would like to know if the GEO proposal should focus on data products or applications for users to analyze their data. My response would be more towards the application. Again, the development of some kind of application that would illustrate the use of big Earth observation data to solve some issue related to sustainable development. Take for example, Sustainable Development Goal 15.3.1 on land degradation neutrality. Perhaps there's some way of for your particular country, or it can be a multi-country proposal as well, how you could use Earth observations to permit your nation or region to submit land degradation neutrality indicators. Let's see, another question here. Are any of the presenters familiar with the work that OneSoil.ai is doing from Belarus, I believe? And it aligns very well with the ideas presented today. Well-designed user interface for end users utilizing machine learning on the back end with a focus on soil data. So presenters, are you familiar with OneSoil.ai?
So let me answer that, Grega from Sinergise. So we are familiar with them in terms of observing what they do and some communication we had with them. And I agree that their technology seems to be well equipped for this task. That being said, for the moment, they were always just showing the results of the technology. So I don't see how this technology could be used by third parties. And I believe that this webinar is meant for third parties to reuse technology to build their own applications. And OneSoil.ai, for the moment, they haven't yet provided this option. So you can just use their application, but that's more or less it, right?
Okay. Thanks very much, Grega. Anyone else online with a question they would like to pose to one of our presenters, or I'll submit in the chat window? Okay, well, if not, then I guess we can go ahead and close the webinar. I'd like to thank each of our presenters again. I'd like to thank Brian Kilo from CEOS on the Open Data Cube, Grega Milczynski from Sinergise on Sentinel Hub, Hamid Ale Mohammed from Radiant Earth on the Stack, and then both Ian Schuler and Amy Barsiakis of Development Seed for their discussion on open source tools. I've recorded this webinar, and unfortunately, Brian, I remembered to do it in the middle of your presentation. So I think it was good that you had a comprehensive summary slide at the end, so that people can know where to go to find further information. But I will check with each of the presenters to make sure they're okay with putting the presentations online. We'll put it on the GEO web page, again, earthobservations.org. And I will also put this recording online. And feel free to come back to me or our presenters. I mean, I don't want to inundate them with questions, but if you've got a question or so, maybe they would be happy to take that as well in an email. So with that, I thank everybody for participating, and we'll look forward to hearing from you if you've got a proposal that you're going to submit. We'll be looking forward to seeing that. Thank you very much, everyone.
Thanks, Doug.
Bye-bye.
Thanks, Doug, for organizing. Appreciate it.
Thanks, Doc.
Bye.
Thank you. Bye.
Bye.